All right, so let's talk really quickly about DNA replication. So we start with the template strand, which is basically the DNA that we're going to copy. And the first step is that we need to separate these two strands from each other. And the protein that does this is helicase. Helicase takes these two strands and pushes itself in between them and forms our replication fork. Oh, this is poorly drawn. Yeah, so now it's like kind of split. Replication fork. As you can see, it kind of looks like a fork because it goes in different directions. But these two strands are attracted to each other, and so they want to close back up, but we don't want that because we want to replicate it. And so we use SSBs, which basically force these two to stay separate, and they do it by stabilizing them. So they will latch on over here on the outside, maybe it's on the inside, I don't know, it doesn't really matter, and basically keep it open. So the next step is that we have our DNA polymerase that wants to start replicating, but it can't. And why can't it? Well, it can't because it is not able to form a new part. Like if you just have a strand, it cannot come on and just start laying stuff down. It can only elongate, that's a key word, part of an already existing strand. So it can take this and keep it going, but it can't start its own. And so what we need is something called a primer. And to put down the primer, or this little basically starter piece that this guy can build off of, we have the enzyme primase. And primase will come in and add a primer. And now DNAP3 can load on and just start going. And in these little drawings, I'm not really focusing on the anti-parallel, like the direction. I'll get to that in a second. So once this happens, once DNAP and primer have basically done their stuff, what we need to do, or actually I'll go over the leading and lagging strand. DNAP can only move in one direction, and that is from the 3' end of the template strand to the 5'. But when we have this replication fork that is opening this way, as helicase opens it further, these strands are anti-parallel. So one of them is 3 to 5, and that works perfectly. This guy can hop onto the primer and just continue indefinitely. But we have this other one, which is 5 to 3, and so we need to be replicating it this way, but the primer, or the DNAP can only move this way. And so they have a little trick for this. The primase will add a primer pretty close to the helicase, and now the DNAP can load on and go from 3 to 5 until it can't anymore. And then when this opens up further, let's say we have this guy move down a little bit. Now we've opened up more, we've revealed more. This guy continues on his track like normal. The primase can add another primer. DNAP can load on again. It basically hops, and sorry this is so messy, and then continue until it hits this first primer. And it continues that until everything's done. Okay, so now what we have is basically these two kind of new daughter strands. One has one primer and then like a bunch of stuff, and then one has like basically just a bunch of primers and then like DNA in between them. So we have a problem, is that we want DNA. We do not want RNA, which is what these are. These are RNA primers. And so we use, let me just label this as 3, since now we're talking about DNAP1. This guy sees RNA and replaces it with DNA. So it basically just tears up this RNA and puts DNA in. And so now we have a bunch of DNA. Here's some DNA, here's some other DNA, then here's all of our Okazaki fragments, as the term is, for all these little parts that were caused by the hopping around of the primase and the DNAP on the lagging strand. But if you tried to read this, like if you tried to transcribe this, it would not work. And so our final protein is ligase. And ligase, ligase, or glues together, fuses all of these little fragments and strands. So now everything is one big piece. And that is done. And you might be wondering, where is DNA polymerase II? I actually asked this question in class because I didn't know. DNAP2 isn't used for replication, it's used for repairing DNA. And that is basically the extent of it, so let's go over a quick review. Helicase opens and continues opening the template strand. SSBs keep the strands open. Primase adds primer. DNAP3 basically synthesizes the new strand off of the template strand. DNAP1 turns RNA primer into DNA. And then finally, ligase stitches all of the parts together. I hope I spelled that wrong. And that is DNA replication.